All right, let's talk 11.4. We've we've talked about inference on two proportions in 11.1 and 12.3, right? When you had independent and dependent samples. And then we've talked about inference on two means in 11.2 and 11.3 when you have independent and dependent samples. Now we're going to talk about inference on two standard deviations. And we only have one test here. So we don't have a separate test for the dependent case. We only have a test for the independent case. So whether the samples are independent or dependent, we're just going to treat them as independent samples. Same kind of thing with the notation. Okay, so if you have a subscript of 1, then that corresponds to group 1. So sigma 1 squared would be the variance for population 1, and S1 squared would be the sample variance. So I guess here I should specify this one's the population variance. S1 squared is the sample variance for population 1, and N1 is the sample size. The test statistic here is actually really simple. It's S1 squared over S2 squared. So the sample variance for group 1 divided by the sample variance for group 2. So really kind of a simple test statistic. However, it follows a new distribution that we haven't talked about before called Fisher's F distribution. And this distribution is super complicated. So even though the test statistic is pretty simple, the F distribution is not. And the F distribution is what this test statistic follows. You're welcome to look at the F distribution in StatCrunch if you want. It's kind of an interesting thing, but you have different degrees of freedom in the numerator than you do in the denominator, and so it's just kind of this crazy little distribution. Like I said, you're welcome to look at it if you're interested. But as far as hypothesis testing is concerned, this works exactly the same way as the other kinds of hypothesis tests we've done. Right? You state your hypotheses, calculate your test statistic, use it to get a p-value. For the two-tailed test, the p-value is pretty complicated on this, so I didn't try to write down the mathematical formula for it. But StatCrunch will compute the p-value for you here, as usual. So steps 2 and 3 are done in StatCrunch. And as always, if the p-value is less than alpha, we reject the null hypothesis. The interpretation of the p-value is still the same as it always has been, right? The p-value is the probability that we would get the sample statistics that we observed if we assume that the null hypothesis is true. If that probability is really small, then we reject our assumption, okay? We reject H naught. The conditions that we have to check. The sample data have to come from samples that are independent. That's not quite true. I mean, you could run this on samples that are dependent, but that is something that the book will have you check for. And then the other thing is that the populations from which the samples are drawn have to be normally distributed. Okay, to run the test in StatCrunch, we go to Stat and then Variance. I think it's actually called Variance Stats. So you go to Stat, Variance Stats, to sample, and then either with data or with summary. Okay, so same as when we were running this hypothesis test on a single parameter, same as when we were building confidence intervals for the standard deviation. I mean, we've been going to the same place over and over again. So let's just take a look at a few examples. Here we have some raw data, so we're going to be going with data. But it says, an investor believes that Cisco Systems is a more volatile stock than General Electric. The volatility of a stock is measured by the standard deviation rate of return of the stock. The data below represent the monthly rate of return between 1990 and 2010 for 10 randomly selected months for Cisco Systems and 14 randomly selected months for General Electric. Excuse me. Does the evidence suggest that Cisco Systems stock is more volatile than General Electric stock? Okay. Well, so I'm going to call the Cisco stock group 1 and the GE stock group 2. And our null hypothesis here, now it says We want to know if Cisco Systems is more volatile. And then earlier on in the paragraph, it tells us that the volatility is measured by the standard deviation rate of return. Well, these are the rates of return down here, okay? These are the rates of return. So the standard deviation of these numbers represents the volatility of the stock, okay? The larger the standard deviation, the more volatile the stock. So if Cisco Systems is more volatile than GE, that would mean that the Cisco system standard deviation rate of return would be greater than that of GE, right? And that's the statement that we're trying to prove. So our alternative hypothesis is going to be that Cisco is greater than GE. Okay. The null hypothesis then, of course, would be that sigma 1 equals sigma 2. Now, when you go to run this in StatCrunch is going to state these hypotheses differently. It's going to state them in terms of the variance, but it's also going to state them in terms of the quotient of these numbers. So it's going to say something like this. Okay, so this is how StatCrunch is going to show these hypotheses. I want you to write them down this way. This is much more clear. But these things are equivalent, right? They're still equivalent. So this number will be 1, and it's always going to be 1. You don't have to change it, right? That's its default setting. So just leave it at its default setting of 1. And then this inequality right here is always going to be the same as this inequality that you wrote down. So if you wrote down a two-tailed test, then this needs to be two-tailed. If you wrote down a left-tailed test, then this needs to be left-tailed. And as we've shown in this case, if you have a right-tailed test here, then this also needs to be right-tailed. Okay. But let's go ahead and do this now. So we're going to go to Stat, Variance Stats, to sample, and we have the raw data, so we're going to say with data. So let's go to StatCrunch and enter all that stuff in, and we'll see what StatCrunch gives us. So let me enter the data in first and foremost. Oops. So I've got some Cisco stock, and I've got some General Electric stock. Okay, so there's the Cisco stock. And then, oh, what is going on here? And then GE. Okay. So let me just double check and make sure that I got all that in there correctly. Man, yeah, just looking at these numbers, it does seem like Cisco kind of has a wider swing than General Electric. Okay. Okay, so let's see what we get. So it's stat, variance stats, to sample with data. You have to tell StatCrunch where the data is stored. I wanted to call group 1 Cisco and group 2 GE. And then we want our hypothesis test. So remember, you're going to leave this at 1, and you're going to change this inequality so that it's right-tailed, just like we wrote down earlier. And then you hit compute. So there we go. We get a pretty small p-value here. Remember, again, that p-value is the probability that we would have collected this sample information if in fact the null hypothesis were true. The null hypothesis in this case is that the standard deviations are equal. So if we assume that the standard deviations of these two groups are exactly the same, then the probability that we would have collected this data, 0.0007, right, which is really tiny. And it's so tiny, of course, that it casts doubt on our assumptions. So now we're thinking, probably the standard deviations are not the same. We reject the null hypothesis, right? So let's write that down. Okay, since 0.0007 is less than 0.05, we reject the null hypothesis, right? And so then in conclusion, since we're rejecting the null hypothesis, that means there's evidence to support the alternative. So we would say at the 0.05 level of significance, the evidence suggests that Cisco stock is more volatile than General Electric stock. Okay. And that's that one. Okay. Let's look at another one. This time we don't have raw data, we're just given some information. So it says, researcher Seth B. Young measured the walking speed of travelers in San Francisco International Airport and Cleveland Hopkins International Airport. The standard deviation of the 260 travelers, who were departing was 53 feet per minute. The standard deviation of the 269 travelers who were arriving was 34 feet per minute. Assuming walking speed is normally distributed, does the evidence suggest that the standard deviation walking speed is different between the two groups? Okay. Before I let you try to work this one out on your own, let me just warn you. I think this problem is almost a little bit misleading because you might think the two groups that you're comparing are people at the San Francisco airport and then people at the Cleveland airport. But that's not true. That's not the two groups that you're comparing, right? You want to compare travelers who were departing to travelers who were arriving. The researcher just so happened to observe people in two different airports, but it's not that he's not trying to compare the people in the two airports. He's trying to compare the people who arrive versus the people who depart. Okay. So I'll let you pause the video and see if you can work that one out. Okay, here's my solution. So I'm going to call the departing group, group 1. And I'm going to call the arriving group, group 2. The null hypothesis is that there's no difference between these two groups. The alternative. Well, it says, does the evidence suggest that the standard deviation walking speed is different between the two groups? So we just want to see if they're different. If sigma 1 does not equal sigma 2. And, you know, well, anyway, we're going to go to stat, variance stats, to sample. And this time we don't have raw data, we have a summary. So we'll say with summary. we'll be prompted for the sample variance and the sample size of each of these things. So the sample variance, right, S squared for the first group, right? So for the people departing, the standard deviation was 53. That means the variance is 53 squared. Okay. And the sample size for that first group was 260. Okay. Sample variance for the second group was 34 feet per minute. So, sorry, the standard deviation was 34 feet per minute, so the variance is 34 squared. And the sample size for that group was 269. So just based on that, I mean, yeah, I would say there's a pretty significant difference. I would be surprised if we don't reject the null hypothesis here, because these values seem quite different to me. But the only way to be certain is to run the test. Okay, so let's go ahead and go to StatCrunch now, and we'll run this test. So in StatCrunch, we're going to go to Stat, Variant Stats, to Sample with Summary. Okay, variance for sample 1 is 53 squared. So 53 caret 2, right? The caret is above the 6 on your keyboard, so you hold down Shift and hit 6. Sample size group 1 is 260. Variance for group 2, 34 squared. Sample size for group 2 is 269. And we want a two-tailed test, so we're going to leave this hypothesis test the way that it already comes in its default setting. We hit compute. And yeah, sure enough, we get a tiny, tiny p-value, right? So we're going to be rejecting the null hypothesis here again. Okay, so let's go back to the notes and write that down. Okay, so since 0.0001 is less than alpha, we reject the null hypothesis. That means there's evidence to support the alternative. So there's evidence that the standard deviation walking speed is different between the two groups. The evidence suggests a difference in the standard deviation walking speed of the two groups. Okay. So I want to think about this with you here for a second, because it's very easy to sort of go on autopilot and sort of go through the motions and write these things down without really knowing what you're doing or understanding what's going on. So let's think about the scenario. When we say that the standard deviation walking speeds of the groups is different, that doesn't mean that one of the groups walks faster than the other. What that means is that one of the groups has a more variability in how fast they walk. So one of the groups has a very, well, and in particular, right, we can see that it's group 1 that has a larger standard deviation than group 2. So group 1, there's a lot of variation in how, in the walking speeds of people. Group 1 was people departing. So there's a lot of variation here in the walking speeds of the people departing, whereas there's not as much variation in the walking speeds of people arriving. And if you think about that, it should make some sense. Because for people departing, some of them may have gotten to the airport, 3 hours early, and so they get to their terminal with plenty of time to spare, and so they're just sitting around kind of waiting for the plane to take off. They're sitting there just waiting to board the plane. But on the other hand, some people may have gotten there a little bit late. And so now they're rushing to get to their gate on time before their plane takes off, right? So you're going to have some people in this group who are just kind of moseying along, and you're going to have other people who are sprinting to get to their gate on time, right? So there's going to be a lot of variability in their walking speeds. Whereas when people arrive, right, when their flight arrives to their destination, there's not as much variation probably because you know, everybody is at the location that they intended to be at. You don't have groups of people having to run to get somewhere on time. And then on the other hand, you don't have people who are there, you know, 2 hours early or whatever. They probably just want to get where they're going, and so they're all walking at more or less the same speed. So that's what this means. That's how we would kind of analyze that situation. Okay. Let's look at one more. Oh, this is a blast from the past. Shoot, I should have saved. We already entered all this data when we looked at the previous section, I think. But and I should have saved it, but now I'm going to have to manually enter all the data in again. Oh well. But this was the space rats example, right? And you'll remember that when we were comparing two means, we ran this example and we found that the mean red blood cell mass of the two groups, we found that there wasn't a statistically significant difference between the mean red blood cell mass. So we weren't able to reject the null hypothesis there. Now we're going to be asked to evaluate their standard deviations, okay? So again, you know, some people sent 14 rats up to space. They kept 14 different rats at home, and when the space rats returned from their flight, they measured they measured the red blood cell mass of both groups. So these were the red blood cell masses of the flight group and the red blood cell masses of the control group. And we already know that their means are not statistically significantly different from one another. But what about their standard deviations? Okay, is the standard deviation of the red blood cell mass in the flight animals different from the standard deviation of the red blood cell mass in the control animals? Well, I'll let you see if you can write down the null and alternative hypotheses and get the p-value and make your decision and all of that stuff. So go ahead and give the video a pause, see if you can work this out on your own. Okay, and here's my solution. I'm going to call the flight group group 1 and the control group group 2. My null hypothesis is that the standard deviation red blood cell mass is the same for those two groups. And then for the alternative, I just want to know if there's a difference. So the alternative is sigma 1 not equal to sigma 2. Okay, so to run the test, we're going to go to stat, variance stats, to sample, and with data, right? We have the raw data here. So let's take a look. So first I need to enter the data into StatCrunch. So we put my kids are outside swimming while I slave away making this video. But they're having to come in and use the restrooms. So you probably hear the toilet flushing in the background and my kids complaining because they're so cold now. Anyway, so there's all that data. I think I've got this all in correctly. Let me just double check real quick. It's looking good. Yeah, okay, yep, I think I've got it. Okay, so let's run the test now. Stat, variant stats, to sample with data. We want to compare the flight and control groups. And we want another two-tailed test, okay. Oh, wow. That's a very large p-value. It's somewhat rare to see a p-value that big, but that's like a huge resounding no, right? Like we're definitely not rejecting the null hypothesis here. In other words, what this is saying is that if we assume that sigma 1 equals sigma 2, then there's like a 97, almost a 97% chance that we would have observed this. Those are really good odds, right? So it doesn't cast any doubt on our assumption. It kind of makes us think the assumption is probably true. But anyway, let's write this down. So 0.9666. Since 0.9666 is not less than alpha 0.05, we do not reject the null hypothesis. So that means there's not enough evidence to support the alternative. Right? At the 0.05 level of significance, there is not sufficient evidence to support the claim that the standard deviation, red blood cell mass, is different for the flight animals than it is for the control animals. Okay. And that's that one. So there's your homework assignment, and we'll see you in 11.5.